Hi, everybody. Got a couple of stray topics to kind of cover, finish up this chapter 13 here today. So I want to talk about three theorems, and then we'll do some problem type examples, and then I don't know if there's more after that. So the first thing we want to talk about is called the fundamental theorem of algebra. I just abbreviate that as FTA for fundamental theorem of algebra. What this says is that all polynomials are solvable, and a polynomial of degree n has n complex solutions if we count multiplicity. So if I have a quadratic, that quadratic is going to have two complex solutions. It's degree 2. I could get two non-real answers. I could get one answer that's repeated twice, or I could get two distinct real answers, right? Yes, Alex?
Are these theorems going to be like using synthetic?
Yeah, that's what we've been working towards. I'm going to do these at the same time. These are two theorems that are basically say the same thing, just with different words, or with one change to them. So I'm going to do like a color thing here. So this is going to be two theorems at once. You read it with the green words, it's going to be the irrational conjugates theorem. You read it with the red words, it's the complex conjugates theorem. This is just trying to save every word. You just read the first words at the slash together and the second words at the slash together. Go ahead. So the irrational conjugates theorem says if a polynomial with integer coefficients has an irrational zero, like a plus b square root c, then the polynomial also has the conjugate zero, a minus b square root c. Or you could read this as the complex conjugates theorem. It says if a polynomial with integer coefficients has a complex zero, a plus bi, then the polynomial also has the conjugate zero, a minus bi. Is everybody okay with how I wrote that? Is instead of writing the same thing twice, I just combined it into like one thing, basically, saving a lot of words there. You know, even without the color blindness, is this understandable of what I did? Yeah. Okay. So I want to talk about a problem type from that 1 through 15 that we haven't done an example of that I want to make sure that we look at. Can I scroll this up? Theorem writers. So I'm going to do two kind of examples here. So the example here says, write a polynomial with integer coefficients, minimum degree, and has the zeros x equals a half, x equals square root 2, and x equals 1 minus square root 3. So if I want to make sure I have integer coefficients, I need to make sure that I follow the irrational conjugates theorem because I have irrational pieces here. So I know I'm also going to have, since I have the irrational 0 square root of 2, I also have the conjugate to it. What will the conjugate to square root of 2 be? Negative square root 2. And what will the conjugate be to the irrational 0? 1 minus square root 3. Nope. 1 plus square root 3. Is everybody okay there? I know I have to satisfy those two theorems. Everybody good so far? Okay. If I'm going to have integer coefficients, so because I had irrational zeros, I got to make sure I also include their conjugates. Now what I'm going to do is I'm going to take each one of these zeros and convert it into a polynomial. So the way I'm going to do that is I'm just going to subtract like the 1/2 over to the other side. That creates a polynomial that's equal to 0. Is everybody okay with that? And I'm going to do that for each of these. I'm going to do something a little weird though with these ones that are like a two-term kind of thing. is I'm going to think about it as subtracting the whole thing as like one number. So I'm going to put a parenthesis around it and subtract it rather than subtract each piece individually. It's fine to do it that way, but I get a little advantage of doing it this way that I'll point out to you later. Everybody okay with what I did there? So now I have, yes?
Why don't we have x equals negative 1/2?
Because 1/2 isn't irrational, right? There's no radical in it, so it doesn't need a conjugate. Good?
Yeah.
Okay. So now I have these 5 separate polynomials, right? Each of them are equal to 0. Agreed? If I multiply them all together, what are they still going to equal? Still going to equal 0. Which is good because that means I still keep all the zeros that I need in my polynomial, right? So far, so good. Now, again, if I apply the zero product property and I break this thing up, I'm going to get these same 5 solutions, right? The ones that I have to have. So as long as I don't include any extra factors, I've got the minimum degree polynomial, right? Does everybody see that? Because I didn't do anything extra. There is one extra little thing though, because if I FOIL this out, what's this 1/2 going to make? I'm going to end up with potentially coefficients that aren't integers, because there might be a fraction. How am I going to fix that? Nope. It's an easy fix. Just going to multiply by 2. Is that okay with everybody? Why would I multiply by 2?
Because 1/2.
Yeah, because I can just distribute that through and now all integers, right? Everybody feel good? Okay, so all I'm left to do now is to multiply this thing together. When I'm going to multiply this together, though, I'm going to pick the factors with the conjugate pairs, and I'm going to multiply those together. So I'm just going to, when I rewrite here, I'm going to rewrite those next to each other. So if I look, I have x minus square root of 2 times x plus square root of 2. What kind of multiplication pattern is going on there? That's a difference of 2 squares, right? I have an a plus b times an a minus b. So when I multiply those out, what am I going to get? Like an a squared minus b squared, right? That's nice. Could I have just FOILed that out also? Sure, but that saves me a little bit of writing, a little bit of work. Now notice that, like the squared's gonna cancel the square root, so I'm just gonna have x squared minus 2, right? I'll rewrite that on the next step. This guy now I'm going to multiply out. Is that a difference of 2 squares? No, because they're both minus, right? And then these parts are different. So what am I going to have to do here? I just have to FOIL. Okay? So if I do x times x, it's x squared, x times negative 1 plus square root 3, and then negative 1 minus square root 3 times x. And then negative 1 minus square root 3 times negative 1 plus square root 3. Is everybody okay with how I FOILed that out? Again, notice I thought of like the 1 minus square root 3 and the 1 plus square root 3 just as like one thing. Just makes my life a little bit simpler to do it this way. Everybody so far so good? Okay. So I'll rewrite that part. I'm going to do some distributing now here. So I'm going to kind of distribute that stuff through. So again, I got to distribute through the negative, distribute through the x. Everybody's okay? And then what do you notice we have right here? It's another difference of 2 squares, right? This is part of the reason why I've kept those things grouped together so I can pick up this. So it should just be a squared minus b squared, right? So 1 minus 3 or minus 2. So I'll put that minus 2. Everybody's still doing fine? Trying to go slow through this so I don't lose anybody. If I'm going too fast, holler at me, Alex.
Is the x, like on the x squared on the left side, shouldn't it just be x squared, or like, is it minus 2?
That's my x squared minus 2.
Why would it be not, well, didn't we cancel out the
The squared cancels the square root, but I still have the 2.
Oh, okay.
Right? Okay. So let's look in here and see for some like terms I can combine. I have a negative square root 3x and a positive square root 3x. Those get to give me 0. And then negative x and negative x is going to be negative 2x. Everybody so far so good? Okay. I'm going to then FOIL these guys together. Everybody okay with what I did there? Just a little FOIL. And now I got to do like this extended FOIL here, right? So basically all I'm doing is making sure everything in the first parenthesis multiplies everything else in the second parenthesis, right? So for example, the first term I'll have 2x to the 5th, and then minus 4x to the 4th, and then minus 4x cubed, and then I'm just going to keep going. One, two, three, four, five, six. Okay. So there I got that. Yuck. But it's just FOIL, you know. All right, now I'm going to combine my like terms together. That's my only to the fifth term. Negative 4x to the fourth and negative 1x to the fourth make negative 5x to the fourth. That's all my x to the fourths. Negative 4x cubed, or positive 2x cubed and negative 4x cubed gives me negative 6x cubed. That's all my cubes. 2x squared, 10x squared, 12x squared. And then 8x and 4x is, or minus 4x is 4x, and then minus 4 at the end. Yes?
There's a question for the theorem. How exactly like, you use the theorem to find like the A minus B, like
This is irrational, and it is conjugate. This is irrational. It's conjugate.
so then how do I the opposite?
A plus b square root c and a minus b squared c are conjugates. The sign in front of the square root is opposite.
And how do you know if you're going to use like complex or use complex?
Is there an I? If there's not, then it's not a complex number, right? Is okay? Let's do one. We'll call this example. Same setup. Maybe that. What? Oh, sorry. Yeah, you should have an x equals there. That's what you're complaining about. I agree. All right. Any irrational solutions here? No, right? Because there's no square roots. Any complex solutions?
Yes.
Yes. Which one is it?
1 minus 2.
Okay. Because of the complex conjugates, I also need to have
And plus
1 plus 2. Do you feel good? Do I need all these ones? Do I need it 3 times? Do? So I'll build my polynomial. Everybody okay with me kind of shortening a couple of steps here? Now that you get the idea of the process, I'm going to shorten some stuff up just so it's not so much writing every single time. But if I do this without writing out what it is, like how we're getting to these the first time through is kind of a maze, right? I want to lay down a lot of breadcrumbs the first time through, and then like just periodic breadcrumbs, I think is enough. Okay. Multiply these together first. And then when you're a math teacher, you can multiply stuff like that together in your head. You do it as 2 phases, right? But when you're a math teacher, you can do stuff like that in your head. This guy will FOIL out the same way we did before. So far, so good. distribute things through, do. And then this is a difference of 2 squares over here, right? What's 2i squared? 4 times I squared, right? And what's I squared equal? Negative 1. And negative 4 times negative 1 is positive 4. So we have a plus 5 there at the end. Make sure you're writing it down. It's not hard, but like it's a lot to carry in your mind, right? Again, you've been doing this for 20 years. You can do all this kind of stuff in your head. It's not a problem. When it's like your first year or two doing that, probably best to do it a lot. It's hard to carry it. If I look in that second set of parentheses, I have some like terms I can combine. So then minus 2ix and the positive 2ix cancel out. And I have a minus x and a minus x. Those can just combine together. And then we just have one more FOIL and we're done. And then we'll combine some like terms. Minus 2x to the fourth and minus 3x to the fourth is minus 5x to the fourth. 5x cubed, 6x cubed, and 3x cubed is 14x cubed. Negative 15, negative 6, and negative 1 is negative 22x squared. 15 and 2 is 17x, and then the minus 5. So again, what's the worst part? It's having to multiply. Like building the polynomial itself, piece of cake. The hardest part, foiling, just because there's often a lot of foils to do there. So last time, we found all the real zeros for a polynomial, right? And I showed you guys how I had to do it back when I was a student, where you just are like kind of flying blind and doing a little guessing and checking, and sometimes you get some good stuff to happen, and sometimes you don't get any good stuff to happen, and you have to do a lot of synthetic divisions. You guys have an advantage that I did not have, the graphing calculator, because you can look at the graph of the polynomial and probably have a pretty good guess as to the x-intercepts, or the real zeros. But there are two situations that still pose a problem. First situation, you have an imaginary zero. Will you be able to see that with the graph? No, they are invisible. There's no hope to see those. The only way you'll be able to identify those is synthetic dividing down to something you can attack using the factoring tree that we discussed in the earlier section. The second situation that poses a problem to us when looking at the graph are multiplicities. That we can help a little bit with. So So we have the bend, bounce, straight theorem. If you have an x-intercept that bounces, where the graph hits the x-axis at that x value and then returns in the same direction it came from, that's a bounce. That means that x-intercept is a 0, and it will be used an even number of times, at least 2. So 2 times, 4 times, 6 times, who knows how many times, but it's going to be at least 2, and it'll be even. If we have a bend, then that x-intercept is a 0 with a multiplicity, or with an odd multiplicity of at least 3. So 3 times, 5 times, 7 times, I don't know how many times, but it's an odd number and it's at least 3. Which is something, right? Tells you that you're going to be able to use that 0 that you found the bend on more than once with our synthetic division, right? That's awfully good to know. And the third one is a straight and if it passes just straight through the x-axis, then that x-intercept is a 0 with multiplicity 1. I'm going to draw this one maybe a little bit better. So what's the difference between a bend and a straight? This is something students often struggle with. So notice how before it hits the x-axis, it's kind of curving like it's going to be a hilltop. And then after the x-axis, it's bending like it's going to be a cup. That change there is like it's called a change in concavity. A point where the graph changes in concavity is called an inflection point. That's what we mean by a bend, is where there's a change in concavity from like hill to cup or cup to hill. Everybody okay with that? And again, easiest to just describe the picture. Right? I don't want to put this all and try into technical mathematical language. The picture is what you're going to look at. That's what you will see. Okay. Let's do an example. right. So let's do our full synthetic division factoring process now. We'll put all the bells and whistles on together so that we can find everything as efficiently as possible. Pretty good. So my first thing I'm going to do is identify how many zeros I'm going to be looking for. The fundamental theorem of algebra tells me I have 4 zeros. Because it's degree 4. I'm then going to identify my possible rational zeros. Well, that's going to be the factors of 35 divided by the factors of 8. So my factors of 35 are 1, 5, 7, and 35. My factors of 8 are 1, 2, 4, and 8. So that's the factors of 7 over 1. And then we'll have a over 2. And then over 4. And then over 8. Everybody's okay with that? Now I'm going to look at the graph on my calculator. Let's do it on the computer, it'll be easier. Okay, so I'm going to turn my calculator on. I'm going to press the y equals button. I'm going to type in my polynomial as it appears on my sheet of paper. Notice that got that in there already. And then I don't know what the last thing I graphed was. I'm going to just do zoom standard. Typically that's enough. If I feel like I'm missing zeros, then I can always address it later on. So I have one zero that's between 0 and 1, and a second zero that's between -2 and -1. And both of those are straights. Everybody agree? How many zeros should I be seeing? 4. I can only see 2. Where are the other 2? Nope. They're not multiplicities because these are going straight through, so they can only be used one time. They're imaginary. That's fine. That just tells me I'll have to end up probably quadratic formulaing or something at the end to get those. Not a big deal. What I am going to do next, though, is I'm going to go through my list of possible rational zeros and discard everything that it can't be. Can it be 1 or -1? Heck no, right? That's not 1 or -1. Can it be plus or minus 5? No, no, no. All those it can't be. Krista? Mm-hmm. Could it be positive 1/2? Yes, but not negative. Luco, what's up?
Understood.
Well, it's in between there, right?
Oh.
So I'm just talking about the range in which that zero is falling, because I'm going to discard everything that's not in between 0 and 1 and between -2 and -1 from this list before I make a decision about what I want to try to synthetically divide. Does that make sense?
Yeah, that's what I was.
Okay. And then plus or minus 2.5, 3.5, and 7 or 16.5 are all out, or 15.5. I don't know, whatever. 12.5. No, 16.5. That's right. Plus or minus 1/4. It could be the plus 1/4, but it can't be the minus. Plus 1.25 is out, but minus 1.25 could be in. 1.75, not positive, but could be negative. This guy's too big and too small. This guy could be the positive end. This guy could be the positive end. That guy could be the positive end. That guy is too small for each. So my possibilities then, if I go to my list, what did I have left? I have x equals negative 5/4. That was it. Oh no, sorry, that's in the wrong spot. That's this one. And then I have x equals positive 1/2, positive 1/4, positive 1/8, positive 5/8, and positive 7/8 were the ones that I had left that fit those intervals, right? Now, if I look carefully at my picture, at this guy, I'm pretty sure it's not any of those right there, right? It's pretty close to the middle. It's not 0.25. It's not 0.125. It's not 0.875. Like, I got a good enough resolution here to be able to discard those ones. But I'm still 50-50 between 1/2 and 5/8. So you know which one I'm going to do the synthetic division with? This one, because there's really only one option. I'm almost certain that's out of work. Is everybody okay with how I spent some time analyzing my graph and making some decisions about what to synthetically divide with? Are these guys always going to be correspond to a number on that list? No, you're correct. Why not? Well, it could be an irrational zero. Like, what if I had square root of 2 as an answer? That's going to look a lot like 1.5, because the square root of 2 is 1.41 something, something, something. Probably too much to be able to tell the difference of when looking at it. So it doesn't guarantee that those are zeros. They're going to be one of the zeros in your possible rational solutions. It could still be irrational, so you still have to check it. Is everybody okay? All right. Here. Okay. Everybody good with us starting synthetic division? That gives me negative 10. 6. No, it's going to give me positive 45. 72 times 8. And that's going to give me negative 90. That gives me negative 28. And that gives me positive 35. So I get a zero remainder. Oos! Now, what did I just show? Yes, but I also did more than just that. That's right, I did do that. But I also showed that this polynomial factors to x plus 5/4 times 8x cubed minus 36x squared plus 72x minus 28. Because remember, this is like remainder, constant, x coefficient, x squared, x cubed. Is everybody okay there? And now if I look at these coefficients, what do you notice about these coefficients? They're all divisible by 4. So I'm going to factor that 4 out. And then I'm just going to distribute it through here. go.
But why would it be x minus 5 fourths?
Because this is like x equals negative 5/4. So the factor becomes like x plus 5/4. Is that it?
Yeah.
Okay. Is everybody good so far? Yes. Uh-huh. All right. Can I factor this guy? Not by hand, right? I'm going to have to do a synthetic division again. The good news is the only choices I have are the ones left here. So I have 1/2 and 5/8. Which one do you think I'm going to pick to try? I think so too. It looks more like 1/2 to me in the picture. And if I got to pick one to try, give me the 1/2 because that's the arithmetic's just a little bit easier, guys. So that works also. Swell. So now I can say I have that, right? Look at that trinomial at the end. Look at the coefficients on it. What do you notice? Yeah, I can take that greatest common factor too. Guess where I'm going to put it?
It's x minus 1.
So I'm going to skip like writing out that step. I'm just going to write this because it's becoming a lot of copying down things, right? Well, I'm just, and again, I'm overdoing it, right? I'm overdoing it so I can see, like this is the first time we're doing this. I'm leaving you the most complete trail of breadcrumbs I possibly can. So when you go back and look at this, it's clear what's going on and what I'm doing and why I'm doing it. Or as clear as I can possibly make it. Like, do I expect you to replicate all of this stuff? No. You can streamline this process as you get more comfortable. All right. So this is now factored completely, right? How do I know I can't factor this anymore? Because the zeros that has to contain are imaginary. Wrong answer. Close enough. Not really. They mean two different things. It'd be like, where are you going this weekend? Grand Rapids? Oh no, I meant Lansing. Whatever, it's close enough. They're both in Michigan. It's like two different places, my friend. All right. So if I want the zeros, though, that's what we're looking for, right? So I can do like the zero product property. So there's my negative 5/4. We knew that already, though, because we got the remainder 0, right? And there's the positive 1/2, and we knew that already because we got the remainder 0 when we synthetically divided again. And then this guy, we can set equal to 0. How are we going to solve that? Yes.
Do you need to have like the two factor ones on the side? Or you just have it like
Again, I'm trying to like give you as complete a picture of what it is we actually accomplished. It'll be, I would be fairly generous if you have like the synthetic divisions and you identify the correct solutions. And if you don't write the complete factored form and it's not asked for that, it would require you to have that. But I want to show you that because eventually this gets stapled on to the factoring tree that we built. So I want to make sure I'm showing you how to take this process and pull the complete factorization out of it, because we're going to staple it onto that end of that thing. Does that make sense? So it depends on kind of what it's asked for, whether you need that stuff or not. So quadratic formula is negative b plus or minus square root b squared minus 4ac all over 2a. 16 minus 28 is negative 12. How do I reduce the radicals? Square root negative 12.
imaginary or 2i.
2i root 3 is correct. Again, 12 is 4 times 3, so the square root of 4 is 2. The negative under the radical makes the I, and then we still have the square root of 3 left. And then I can reduce this by just thinking about it as 2 fractions with the same common denominator. So I have 2 plus or minus I root 3. So one solution here, second solution there, solutions 3 and 4 here. Why is this counting as 2? Because of the plus or minus. Ta-da! Yeah, so that takes a minute, right? How many of these do you think can appear on your test? Yeah, 1 or 2, right? Like can't be more than that. All right. I want to point out to you now, if we go back and think about that factoring tree that we drew here, we had all these stops, right? Yeah. So now before we can stop, we also have to check to see if there's a synthetic division thing. Right? Now, you may encounter problems on your test where I just ask you to solve the thing or to find the zeros. And even if it's something that like you could have done by grouping, but you missed that and somehow just do synthetic division on it, are you going to get the right answers? Yes. Yeah, you will. The synthetic division will catch. Like if you missed, like, oh, I thought this was, I thought this was not in the quadratic form. It turned out it was. I did the synthetic division and got solutions out of it. And it could have been done this way. Is it going to catch those answers? Yes, it will. It will. So, like, it's kind of nice to staple that on to this process and think about this as all part of still doing the same thing. Now, is this synthetic division process an end-all, be-all? It's going to work for every polynomial. I can easily give you a polynomial where this synthetic division process is going to fail as well as these fail, right? In fact, solving a polynomial is a really important piece of mathematics that there's a lot of research being done and still being done on, because there's a lot of real-world application built around these solving procedures, most of them related to cryptography. What cryptography is? Yes, like code breaking. So you send a text message on your cell phone, right? And you're sending this across a public network. Presumably anybody with the proper equipment could intercept the signal and look at your text message, right? What prevents them from doing that is that your text message is encoded. And one of the methods that we use to encode a text or any kind of message sent over a public network requires you to do a prime factorization of a large number, like a potentially 1,000-digit long number, and break that into 2 prime factors. Now, there's not a fast procedure to do that, which is what creates the security, is it takes lots of computers working in parallel a lot of time to be able to solve that problem. To break your encryption, if somebody wants to read your text message, they're going to read it. It's just going to take them a month before they're able to do it. And at that point, you're hoping that it doesn't matter anymore. But the methods that you're using to do a prime factorization for a number are the same methods that we would use to factor a polynomial, which are really the same that we use to solve a polynomial. So this area of mathematics is really an important one. As you imagine, there's a lot of organizations that would be really interested in being able to break encryption, namely the governments, right? Yes. It's not just to spy on its own citizens, but also on enemy nations, you know. But they'll spy on you too, don't worry about that.
Oh, I feel so loved.
No, my data. No, I would use that.
Okay? Everybody feel okay with what we've done? All right. This allows me to assign the final block of problems, so 36 to 53. That'll be part of not this Sunday's problem set, but the following Sunday's problem set. So before you get back to school from break, that's when the 36 through 53 is going to be. Yeah, that's some dyslexia right there. 35 or 53? So 1 through 35 is this Sunday. 36 through 53 next Sunday. What haven't we done yet?
Homework quiz.
Homework quiz. How many more class days do we have before break?
One.
Boy, what do you think is going to happen? What else is going to happen on that day considering we just finished the lessons?
Review.
No card and review, yes.
So we can test the first day back?
We'll probably do it the second day back, because I'm, as much as a crazy man as I am, I'm not crazy enough to ask you to do a test the day you walk back from break. That's a little rough. I'm a crazy guy, but I'm not that crazy. So we'll find something else to work on, maybe just like a Delta map to review some of these topics and then do the test at home class. It's kind of what I was thinking. Does everybody feel good about due dates? What's on the table? What's happening when? If you're looking to prepare for your homework quiz, I would know how to use my calculator. Find zeros, find maxes, find mins on my calculator. We talked about that the first day. You should be able to do that. And now I'm going to shut up and stop talking.